My name is Rana Kazamal, and I'm a director of product management within the mass infrastructure business. So let me start first by, quite simply summarizing what routed optical networking means, right? So if you take a look at how networks are built today, we've got three-tier type of networks. So we've got a layer of IP routing that does switching in the MPLS domain. Then we've got a second layer of OTN switching that basically is carrying also other types of services like private lines, for example. And then beneath that, we also have another third switching layer for ROADMs, where you can switch in the optical domain. And as you can see, like to build such a network is quite complex. It takes a lot of CapEx and OpEx, but also the fact that if you want to troubleshoot, you need to look at 3 different layers, which is also, kind of redundant. And, moving forward, we can completely simplify this and moving towards a single layer network with a single control plane. And that's what we call routed optical networking. So you basically can start leveraging some of the new technologies like integrating pluggable optics into the routers. So you can start the optical domain within the routers themselves, leveraging innovation in segment routing and EVPN so that we can leverage a superior control and forwarding plane mechanism. And with the full programmability that's built in, automate from a single pane of glass the multi-layer networks that exist today, but also the new routed optical networking as well. And as you can see, by doing that, you can significantly reduce the number of platforms you're using, which means that you're reducing your CapEx and your OpEx, you're reducing your space, your power, and also because we're basically driving a more efficient architecture, we can even drive higher fiber utilization on each wavelength, and basically allow you to get the maximum out of that. Everything that we're going to be talking about today is based on standards. So we leverage open APIs. We take part in a lot of interop in the industry to make that happen as well. And some of the savings you see here are also like proven in an ACG report that you can refer to that's publicly available.
I want to define a couple things because we didn't really define what they were and folks might not know.
Go ahead, please.
OTN meaning, optical transport network, like, your DWDM equipment, your wave division multiplexing gear that allows you to run multiple wavelengths on the same fiber. And then ROADM, which is a reconfigurable optical add drop system that allows you to do the optical switching. So I think that's sort of foundational that some folks may not have knowledge of. So I just wanted to define that.
So basically, if we kind of take a look at the market transition and look at some of the economics that enable us to make that shift. So if we take a look at how we've been building networks, usually what we do is we try to optimize the number of router ports because if you look, for example, at a 10 gig type of network, the router ports are more expensive than, let's say, the optics that plug into them. So what we usually do is we have multiple switching layers. There's switching that happens in the IP domain, and then you've got switching in the optical domain as well that you basically do to try to make sure that not all the traffic goes up to IP, so you're reducing the number of your ports, right? Now, if you look in the 400 gig era that we're kind of embarking on, that becomes the total opposite because the actual price of the optics actually becomes even more expensive than the price of the router ports. And the reason is that there has been huge advancements in routing silicon that is really exponentially decreasing the dollar per bit that you get. And with some of the latest routing silicon that we have, we're basically able to build systems that are, up to 260 terabits of traffic that can basically even surpass the traffic demand. And that's like for the first time in a single chassis, you can do that. And as a result, you can actually have space to do more switching in the IP domain and simplify and converge your network layers. Now, there's also, if we look at the optical domain, there also has been innovation in the space. So typically the transponders, which are really the elements that do the convergence, they converge basically or convert the DWDM signal. Basically, those were traditionally like transponder shelves. Those have been kind of revamped where we can actually just have a pluggable optic that can do the same functionality, and you can plug this into the router, completely eliminating the need for those bigger transponder shelves. And basically, if you're going to go for very, very higher distances, like maybe 10,000 kilometers, like subsea type applications, we can have much more compact transponders, like 1 or 2 RU type systems.
Are you talking about pluggables here that would be coherent pluggables? And if so, can you maybe go into some of the form factors in use here, CFP2, or how you're handling power and cooling and all those common problems with coherent?
Yeah, exactly. So basically, they are coherent optics. We basically have 2 form factors. There's the QSFP-DD, and then there's the CFP2 type as well. And basically, we've been kind of integrating those. And the nice thing about QSFP-DD obviously is that you've got the same form factor as traditional optics. So you basically don't need to have like a density trade-off by reducing the number of router ports, right? And we're going to talk about that next as well. So the last thing that I just really want to call out here is, basically the need for coherent technology into routing is going to become more and more prevalent, because if you take a look in 400 gig, if you want to do anything above 10 kilometers, you need coherent technology, right? So you no longer can do this with gray optics anymore. And as we go to, just laws of physics, right? As we go to higher distances, higher speeds, the distances that we can do without coherent is going to become less and less, right? So if you take a look here, this is a forecast from Signal AI on the exponential increase that we're going to see in coherent ports moving forward.
Can you go back real quick? So
Sure.
when you start talking about the longer range, long haul, and subsea, along a optical, a DWDM network, when you get past the distance that the optic supports, the transponder supports, there's an amplification chain that needs to happen. So this is different kind of equipment, basically amplifies the light levels. How do you deal with, or can you deal with amplification chains that are non Cisco vendor? Can you run as alien wavelengths? Can you
Exactly.
Are you going to talk about that a little bit later, or?
I will definitely talk about that, and that's exactly what we basically are saying is you actually don't need to change even your optical network today if you've got existing ROADMs with the all the design you've got in the optical domain. You can just plug in those 00 plus optics onto the router and run them as alien wavelength over those existing optical systems, right? And that's kind of the beauty of that, and we're going to talk about that next.
Okay, and why that's important is because replacing those is non-trivial, and their mean time to replacement is typically at least 10 years. So being able to back into that is very nice.
Exactly. And we've been doing a lot of testing, a lot of deployments over actually multi-vendor scenarios, like let's say existing ROADM networks that are non-Cisco today, across multiple vendors with a number of our customers. And we're basically like really able to do this. And, there have been press releases about that as well.
Excellent. And just to define alien wavelength, because I kind of dropped that, and it's a wacky term that no one's going to know. Basically, that is running an optical wave from one system on a different system, where you may not get the same type of information within the shelves. So it's essentially like a plumb through wavelength that isn't from the same vendor as what's may also be along the path.
So it seems you're eliminating the need for transponders on the optical shelf. Now, my question is, what's the solution if the range is very long that needs regenerators? So what's your solution? You have to put a router there?
Yeah, so they're basically, so this architecture is quite flexible. So there's multiple ways to do this. There is, basically when we say we're eliminating the transponder shelf, we're still doing the transponder function, but in the pluggable into the router, right? So if you need to keep your existing optical design as is, the amplification you're doing, the regeneration, the ROADM switching, you can basically continue to do that as is today with minimal disruption to your existing design. Now, moving forward, we're going to talk next about it, but as you move to like further phases in this journey, you can decide to simplify further and basically, move switching from like ROADMs into the IP layer to have a unified control plane, and then you can do regeneration as you said, in subsequent router nodes. But again, that's not mandatory. We can, today leverage whatever is existing and just run over it. At the end of the day, the 00 plus optic is a transponder, right?
So when I think about the power envelope of what I can put into an SFPDD port and how I can cool that in my router and all of those things, it's not a lot. And when I think about the transponders I have, which are 2U devices that are using kilowatts of power, not watts, how is that being solved?
Yeah, so we've been already doing this, right? So we've been able to integrate, like we've catered for the cooling, the power within the chassis. We're able to put the 00 plus optics into the routers and basically cater for that. So this is like work that was already done, but as you said, obviously that needs like close engineering to make sure that the power and the cooling is done properly, and you can get that for sure. Yes.
And does that mean that perhaps I need bigger amplifiers external to the router as part of my optical system, and then kind of moving that, so I still need maybe some additional equipment on my optical system?
So there are two phases of this. The phase that we're in right now, so that's the very first generation of the 00 plus optics, right? So the ones that run in the QSFP-DD form factor, so the exact same form factor as your gray optics, those are minus 10 dBm, right? So basically, you can then use an amplifier after to get to the 0 dBm, right? Now, also first generation technology we have today, instead of QSFP-DD, we have a bigger form factor, which is the CFP2 DCO, right? Which basically, because it's a bigger form factor, you can basically amplify and you can basically have a higher launch power. Now, next, what's going to be coming next is even on the QSFP-DD, we are going to have the 0 dBm launch power come out of it as well. So obviously that will drive, the benefits of both, which you've got the smaller form factor and the higher launch power.
When we have to start moving off of the grid and onto solar and wind to regenerate the batteries at a cell site or somewhere like that, how does this architecture translate versus, using power efficient devices and passive optics, passive shelves, where, power is a constraint? Is this the right solution for that? And is it possible on, when you're not using street power?
Yeah, I mean, like if you're gonna be using, let's say if you want to use like, passive technologies, again, anything that you're able to do with transponders today, you're able to do here. Like there's nothing that kind of prevents you from that. If you want to use like passive muxes, demuxes, and so on, and we can have just like, for example, fixed, wavelength type optics, we can do that as well.
Okay, but I guess to refine my question, if I'm gonna, instead of putting a passive shelf in a router or an L3 switch out at a cell site, for example, if I were to put a converged device out there, what does the power look like for that as it relates to using not grid power when you're using DC power on solar and wind? Is that anything you guys are looking at? Just because with the advent of 5G and all of the explosion of towers and RF resources, and especially the optical out to the 5G, which we just talked with someone else with Cisco about, that's just a big challenge from a power perspective. And I don't know if that's something you guys have tested or tried. I guess that's more of my question is, have you guys tested this with, alternative power?
Yeah, so I think whatever power we support on the routers today, it's the same, right? So we have AC, we've got DC options. So, whether you've got the pluggable in or not, that's kind of not related to the power source itself on the router. So whatever we are supporting there can be done, right? So we've got, AC, DC power type of versions on the routers. So just to quickly summarize, we've got, 4 pillars on what we're building on that we believe really is fundamental for the Internet of the future. Obviously, the massive scale silicon we spoke about, we can scale now to 25.6 terabits of traffic. And we've been kind of launching silicon, quite fast recently with the new innovation we have. Building systems optimized for 100 and 400 gig, whether it's custom silicon or merchant silicon. We've got quite a diverse portfolio. On the software side, a lot of innovation within the iOS XR system, SR, EVPN, programmability, but also on the automation stack that basically allows us to manage the multi-vendor, multi-domain, multi-layer type of network. And in the optics space, we've been developing a lot internally, but also making acquisitions that enables us to be kind of leaders in that space. And To talk about some of them, Cisco has been doing billions of dollars of investments in various, basically, whether it's startups or well-established companies. And as you can see here, like whether it's on optics, with the likes of Core Optics and Lightwire, like Stera, and then recently Acacia. Acacia was over a $4 billion acquisition, and they're leaders in the Coherent Technology that basically completely enable this architecture we're talking about. Or also in the routing domain with the Liba acquisition we've done years ago, that really is the foundation for Silicon One and how we're able to drive next generation silicon that is basically higher than anything in the industry today. On the automation side as well, so we've done a number of those. So Carradine for the unified capacity planning capability, TLF acquisition for orchestration, where we're actually able to orchestrate complete multi-vendor networks. And this has been going on for years, deployed on a lot of the service providers globally, and the recent one on Sedona Systems. And we're going to talk about that today, which really does hierarchical control over an IP and optical network, completely multi-vendor, multi-domain, and allows you to basically have that single pane of glass across the whole network. Now, if we kind of talk about why now and why IP and optical convergence, we actually spoke about, quite a number of those based on also the questions that came in. So like we spoke about, we can plug in a 00 plus optic, same form factor of QSFP-DD into the routers, which means that you no longer need dedicated types of line cards like we had previously, right? Where we had to put the DSP on the line card itself, and as a result, reduce the port density on that line card, and hence the cost of the overall solution was expensive. Also, we're getting much more mature in the industry. 00 plus now is standardized, interoperable, and previously that wasn't the case in the previous iterations of such technologies of IP over DWDM. The massive scale silicon that we spoke about, coming with Silicon One from the Liba acquisition, the manageability of IP and optical with Sedona and what we build within Crosswork automation, along with the significant TCO savings that we see there. And as we spoke about, so today you can start by moving from this 3-layered architecture, move to simply just plug in the 00 plus into the router so that you can basically eliminate the transponder and keep your optical design as is. And basically over time, you can move to the simplified single control plane based architecture. And if we take a look at IP and optical networks today, we basically have an IP routing layer, which is running typical services like business VPN, mobile, residential, and basically underneath that, you've got your optical layer, which basically has its own switching domain. So as you can see here, like typical aggregation core networks have a full mesh switching layer that does a separate control plane. And basically, like over this network, we've got also services like private line, OTN type services that are carried over. Now, the challenge with this is you've got a completely siloed network. You've got different operations team operating each one of them. You've got automation tools that are again siloed for each one of that layers, and then you basically then have an inefficient network design, right? So you've got inefficient capacity planning because you're doing it separately on IP and optical. You've got complex operations, and you're basically not really optimizing for that service end to end because you're treating each layer separately.
So one thing that you can do, especially with like long haul transponders, where you're doing what I've heard called inverse multiplexing, basically at the OTN layer, where you're able to run, let's say you have, from the OTN layer, you have 1 by 200 gig and 1 by 600 gig. Well, on a lot of platforms, you can't actually split that up to be 2 by 400 gig. You would have to do 8 by 100 gig. Is there any way to do that in a converged optical system like this? Because you're kind of losing OTN and the flexibility that gives you. So is that just kind of a trade-off you have to acknowledge when you're going to RON?
Yeah, so basically, like if we look at what we're kind of proposing, like today, it's probably very hard that you're gonna find like an 800 gig OTN service towards like an end customer. As you know, like majority of the private line services are kind of lower speed. So basically, what we would be proposing is at the actual endpoint in the network, you can then just terminate that OTN service towards, let's say, that business customer, and you don't disrupt that interface, but you're actually able to then run that over the IP network and benefit from the statistical multiplexing that you have within IP as well, right? So you're basically able to carry that traffic from OTN type services over the same IP network with all your other services on mobile, residential, so on and so forth, right? So you basically actually get better capacity utilization and better statistical multiplexing by doing that.
You said carrying OTN over MPLS. It's never efficient technology, basically, because you're carrying TDM over an IP network. So you cannot really get the benefit of statistical multiplexing anyway, because you need to reserve bandwidth for the MPLS network. But is this something you're proposing?
So we call that, private line emulation, and we call that also SR circuit style, which basically enables you, yes, you can, because you're running that OTN service over an IP layer, you can still do the same bandwidth reservation that you're used to make sure that the bandwidth is reserved end to end and you've got an active and standby, but you're actually doing that via an SDN control, which means that you can still run other services as well over that same exact network, right? So you basically get the benefits of both worlds. And with that, if we take a look at this, like we can drive this huge network transformation into a phase approach. Today starts with where we are today, where we're integrating transponders into the routers, running over existing optical systems. The second phase can be that what we just spoke about, which is we can converge those private line services over the IP domain, get rid of that OTN switching layer. And then the third phase can be driving even further convergence by driving a simplified architecture and converging the control planes as well to have unified switching, right? Now, if we take a look at how this looks like, visually, this is how an IP and optical network looks like today from a physical connectivity. You basically have got your routers. You have to plug in a gray optic to connect to the transponder shelf, which actually has another gray optic, right? And if you remember what we spoke about, as we move to 400 gig and beyond, the price of those optics actually become expensive, right? So what we can do in the very first phase is we can simply eliminate those two gray optics on every link and the transponder shelf itself, and basically replace that with a ZR0 plus optic that plugs into the router. And that can basically run over your existing optical network as it is today. And you can start with this phase today. And we've been already doing this with a number of our customers. The second phase of this journey comes when you start to integrate the OTN services as well, right? Where you can basically move those private line services into the routers, and you can eliminate those OTN switches via the technology we call private line emulation. Now, if we take a look at what that really means is we are emulating how you can run circuits over the IP network by maintaining the same characteristics of bandwidth reservation, ensuring that the path is bidirectional, that it's persistent and does not change. So all those characteristics can be actually built in with the new innovation that we're driving on segment routing circuit style. And at the same time, you're basically keeping the same end circuit towards the customer, the OTN interface, which means that the service providers can then maintain the higher revenue services while reducing their CapEx and their OpEx spend. And in addition to this, we're actually spending time and effort in the automation stack and within the network as well in terms of visibility to ensure that we can even enhance the SLA further. We can enhance the assurance over this network to give a superior performance. And it's obviously much easier to troubleshoot because you've got a converged network with, you're eliminating the layers. And basically, we've got a full automation stack that can give you complete visibility on your service.
So when we've looked at things like this in the past, now granted it's been a handful of years since we investigated the packet optical avenue. One of the things that we noticed was that when you have an OTN platform, the amount of information that you get back from the transponders is extremely rich. There's lots of stuff you can grab out of there. Does that change at all by moving that down into the router? Are you still able to get all of the information you would get out of your transponders, or at least close to that, from running it in an optical platform? Routed platform.
Right. Yes, exactly. And basically what we've been doing is we've been enabling not just like native models, but we've been working on the standard-based models, open config-based, where we can basically send via telemetry all the KPIs that you would need from the router on the transponder, which is basically the pluggable into the router. And basically we're enabling the full automation of that because we're having a hierarchical controller that can stitch between the IP and the optical domain to make it very easy to operate this network. So we're definitely enabling the same level of those KPIs and visibility into the network. And even more, I would say even more with what we're doing around the IP and optical integration that I'll talk about next.
You said the launch power of the ZR optics is -8 dBm. So here's an issue, basically. If you want to transfer that as an alien wavelet, the ROADM networks that we have are not optimized except that launch power. So what are you doing basically to optimize that?
Today, there are two things. So if you use the QSFP-DD form factor of -10 dBm, we basically can have, and we've done this over existing optical systems, you can basically amplify and basically kind of raise that to like a 0 dBm type of launch power. Or you can use today a CFP2 DCO optic, which can do the higher launch power that you're asking for. Now, in the near future, we're going to be launching as well a 0 dBm 00 plus, which with a QSFP-DD form factor, right? So you're not going to need to even worry about that launch power, even in the small form factor.
In the previous slides, can you go back, please? So enhanced SLA through the segment routing circuit style. Can you just elaborate a little bit on that? So you are reserving the bandwidth, I think, and then how you are enhancing SLA. Can you just?
Yeah, so this takes me to the next slide that I'm about to get to, but basically, like so obviously we're mimicking everything that you can do today on OTN type circuits. We can reserve bandwidth. We can basically have the full visibility and maintain the basically the assurance, but we're actually building more than that, right? So we're building not just a view over a single network layer, but we're doing it all the way down to the fiber, right? So we're making sure that those services can run over diverse geographic paths, because as you know, a lot of the outages that actually happen due to fiber cuts. We're also able to do things like predictive analytics and predicting failures and basically solving them before they happen, because we are basically looking at things like PM data, prefect bit error rates, and we're able to basically anticipate if there is a failure, as an example, and then we're able to kind of remediate that. So we're kind of focusing a lot on the automation side to make sure that we are having a much more simpler to operate network, but can also do a lot of the proactive remediation, closed loop automation use cases, and ensure that you are basically, avoiding failures before they actually happen, right?
That's why I think there was an intent-based keyword in the previous slide also.
Yeah, and the intent-based thing is everything that we're building, we're looking at the service, right? So we're no longer like in our controllers, we're no longer just like saying, okay, look, we're going to send you the bunch of alarms, right? And give you the visibility of the network and you deal with it. No, we're actually kind of starting from the service down. So we would tell you each service, is it degraded? Yes or no? If it's degraded, why? What's the root cause analysis behind that? To make it much easier to operate, instead of like today, you're getting a bunch of alarms and you have to, figure out, troubleshoot where the issue is, which layer of the network is that. And that's really the power that routed optical networking brings. The operational simplicity is a big part of it. So basically here, the last phase we were talking about is if you need to, I mean, again, if you don't need to or you don't want to, this is not mandatory as part of the architecture. As you said, it's a phased approach, and every customer can choose the path. And we do a lot of TCO models working with our customers to see what's the best fit for them. But then moving forward in the future, you can also start thinking of reducing the switching that you're doing in the ROADM layer, and basically move all your switching towards a very simple network that is basically hop by hop, and consists of those building blocks we spoke about, right? Super high density router that can switch everything required, converge all services, your 0/0 plus optics, a simple DWDM system which can either do just MUX demux amplification, or can also do ROADM switching if required, and the automation stack that gives you all the assurance, analytics, optimization based on the service itself, along with the full network visibility, and allow you to do capacity planning efficiently over this multi-layer network, or the raw network that we see here that is a converged layer network. Now, from an automation stack perspective, this is kind of the stack we've been building, and it's fully standard based, aligns to like IETF ACTN architecture that says you've got an IP domain controller responsible for automating the IP domain. In this case, it's our crosswalk network controller. You've got an optical network controller that is responsible again for automating the optical domain that we call the Cisco ONC in our portfolio. And then you basically have a hierarchical controller on top of them that is able to give you that single pane of glass, do all the multi-layer use cases, automate across IP and optical through those domain controllers, right? And everything that we're doing is multi-vendor, right? So whether it's the IP domain controller, fully multi-vendor, or the hierarchical controller that can talk to any third-party domain controllers, whether from other IP vendors or other optical vendors, to give you that single pane of glass across your whole network. We're also doing capacity planning unified via WAY, and unifying the device lifecycle management through EPNM. Now, if you take a look at as customers are moving to this architecture, we need to cater for various deployment scenarios, right? So there is maybe you're going to start with this in one part of your network, and basically deploy it side by side with your brownfield network. So we're able to actually automate both of them seamlessly and enable you to do those migrations. And you can even, as we said, you can just start with the routers and the pluggables running over your existing optical systems as they are today. And we are then able to give you complete visibility across them end to end, so you can manage this quite efficiently. Now, if you kind of take a look, and the power of this really comes from the fact that you are really able to start at the service layer and know exactly for each service how that maps down to, let's say, your SR policy, down to your IP logical topology, down to the physical connectivity, down to the optical domain, and also your fiber, right? Having that complete visibility end to end and doing correlation is extremely powerful and makes the network much more easier to operate. And then for the IP domain, we've been kind of building a holistic controller. And this was actually coming from operator feedback on what they would like to see to be ready for the 5G era. And it's really around doing everything from service provisioning to visualizing the complete topology, to doing optimization for SR, SRv6, but also RSVPTE-based networks, the ability to do service health and service assurance that we spoke about, starting from the service itself, and obviously zero-touch provisioning, along with a lot of the closed-loop automation use cases. And then finally, we get to our capacity planning tool, which, as we said, it's super important that we're doing this across both IP and optical, so you're not doing capacity planning in a silo. And this allows us to basically ensure that the CapEx spend that you're actually putting on the network for any of the new services is actually optimized and not like being redundant, layer over layer to make it more efficient. So this is some of the market traction that we basically, we've got a number of customers that we've deployed with and tested with. And this is some of the public references that we had. Windstream, for example, talks about how actually the ZR+ technology proved to be applicable to as much as 80% of their existing links, right? And this is a huge cost savings. If they're able to move 80% of their links to this technology, it's huge cost savings compared to the price of a transponder today. Telia, for example, is we've got a number of press releases and white papers that also Telia was publishing, where it really shows how they were able to run the routers with the 00+ over their existing optical vendor as is, and basically kind of lead with this new innovation. Colt has been doing that, but also adding automation capabilities as well, leveraging all the SR capabilities. And again, we've got a number of those, and this is just a quick peek view of some. And to basically summarize the benefits of routed optical networking, it's both a CapEx saving because you're eliminating network layers, you're eliminating those gray optics to connect transponders, you're integrating the transponder into the router, and you're also completely eliminating an OT and switching layer that you don't need to spend on separately, right? So you get a lot of space, power, operational savings as well, and you're really able to kind of have a much more simpler network to troubleshoot. You can see there's a lot of OpEx savings. This is just a snapshot from the available white paper that you can download. It's publicly available. And you can really see like the comparison of the network models and where all those savings come from in more detail. And lastly, like just to close with some key takeaways, as we said, this architecture has proved to be saving up to 45% TCO savings. You can start today with the very first phase of replacing transponders with ZR+ optics and run them over your existing optical network. And then over time, move to an even further, more simplified architecture, leverage all the innovation in routing silicon and optics and automation that we have today, and simplify your network with a single control plane that has all the services running over that same network. And then lastly, to enable the seamless migration and the seamless operations, Crosstalk automation really allows you to simplify that. You can manage your existing brownfield network and the RAN network from the single pane of glass, and be able to do everything from orchestration to assurance to path optimization. And we've got a complete stack around that, and we're also publishing design documents and white papers to cover that in depth.